All right, so let's now take a look at how we can compare the values of Q and K to predict the direction of a reaction. Okay, so we're going to compare Q and K to predict direction of a reaction. So is it going to go towards the product side? Is it going to go towards the reactant side? Or is it actually at equilibrium? So we have this problem here. It says at 375 degrees Celsius, the equilibrium constant here for this reaction, so Kc is 1.2. So we're told what that is. It says at the state of a reaction, so at a particular point in time, in other words, the concentrations of the N2H2 NH3 are as follows. So we're told that the N2 is equal to 0.071, and these are all in molar. I'm just going to omit that for right now. Our H2 concentration is 9.2 times 10 to the negative 3 molar, and then the NH3, the ammonia, is 1.83 times 10 to the negative 4 molar. Okay, and then it says determine whether the system is at equilibrium. If not, determine in which direction it must proceed to establish equilibrium. So the first thing we can do, double check that your equation is balanced. Okay, and then a quick check of it, we'll see that yes, it is balanced. Then we can write the QC expression, the reaction quotient expression for this, and we're going to use the balanced equation to do this. So QC here, we the product, so NH3 raised to its coefficient, which is 2, so NH3 squared, divided by the N2 to the first power times H2 to the third power, because those are their coefficients. All right, and then all we're going to do is going to substitute these values now into our expression. Okay, and then we're going to write this up here on the right side. So QC would be equal to NH3. That was 1.83 times 10 to the negative 4. Okay, and that's squared divided by the N2, which was 0.071 times the H2, which is 9.2 times 10 to the negative 3, and that's to the third power. Okay, so really what this boils down to again is just a math problem we need to solve for QC, right? What is that value after you plug these numbers in? And again, it may seem simple enough, but oftentimes students have trouble with just how the calculator works. Make use of your parentheses, okay, when you plug these into your calculator, because your calculator will only do what you tell it to do. So if you're telling it to do something incorrectly, you will get the wrong answer, right? So when you plug that in, you should get 0.61 as your value for QC. We're going to compare that now to KC, which we're told at the beginning was 1.2. So simple comparison here of numbers, we see that our QC, our reaction quotient, is less than KC. Okay, so that means according to this scenario, at this point where we measured QC, the product concentration was less than what it is at equilibrium. So that means then this reaction will proceed. So reaction, it has to proceed to the right to increase the concentration of the products to make the QC large enough to be equal or to eventually get to the equilibrium constant. So we say the reaction proceeds to the right or to the product side. Okay, and we established that when we summarize the differences. So if Q is less than K, the reaction of the system proceeds in the forward direction, which is to the right side. Okay, so in situations like these, okay, you will need to calculate one of these two things, either the QC or the KC. We need to compare them, and it's a very simple comparison. If QC is equal to KC, the reaction is at equilibrium. It will not proceed in any net direction. If QC is less than KC, reaction will proceed to the right, to the product side, or in the forward direction. Okay, all of these mean the same thing. Okay, and then if QC is greater than KC, the reaction will proceed to the left, to the reactant side, or in the reverse direction.